Okay, so chapter 7, we're going to talk about security in transit. We're going to talk about HTTPS, TLS, and also SNI, service name invocation. So first, section 7.1, we're going to enable HTTPS or TLS termination for single host using Istio gateway. So take a look at this diagram here. The connection from the internet goes through a internet gateway inside AWS VPC. If you're using AWS EKS, if you're using GKE, then it'll be different. Then traffic goes to classic load balancer and also Istio gateway service, and then eventually goes to Istio gateway pod, within which a standalone Envoy proxy is running to do layer 7 load balancing. What we're going to be doing is to enable TLS connection from internet to internet gateway to load balancer to service all the way until standalone edge Envoy proxy inside gateway pod. So to do that, we're going to be providing TLS block with model simple and a credential name. This is the Kubernetes secret name within which TLS certificate, server certificate, it is stored. So what we're going to do is to create TLS certificate, and then after that, store that in a secret, and then modify this gateway YAML file to enable HTTP connection. First, step 1, create a TLS certificate. Since we have no DNS binding for this example on the demo, we don't own any DNS host domain. So what we're going to do is to allow any DNS host in certificate. So we're going to be using asterisk wildcard.eob.amazon.aws.com for TLS certificate host, which is this one. This is a common name, eob.amazon.aws.com. This is only if you're using Amazon EKS. If you're using GCP and also GKE, then load balancer's domain name will be different. If you're using Microsoft Azure, it'll be different as well. If you're using, let's say, Minikube for local Kubernetes cluster, this is going to be different as well. So make sure to change this one according to your environment. Basically, we're going to use this OpenSSL command, create a certificate with a common name, eob.amazon.aws.com for our case. So this dash new key argument is going to specify algorithm, encryption algorithm to be 2048-bit. Could be 1024 or 2048 or 4096-bit. We're going to choose 2048. It is dash key out. This is going to specify name of private key. So it's a .key.pem. And dash out, this is going to specify the name of server certificate name. So it's ending with the .cert.pem. Dash days, and this is going to say it's going to expire in 365 days. Dash subject, we're going to define common name. This is where we specify domain name for certificate. We're going to use asterisk because we don't own any other domains. So we're going to copy this command and paste in here, enter. It's going to create a 2048-bit RSA private key and it's created. So let's ls enter, and we should see 2 files created. So here is still eob amazon.aws.com cert pem. So next, what we're gonna do is we can check the content of the cert that just got created. So grab this command. Basically, it's doing OpenSSL x509 and a dash text dash no out. Dash text is gonna show the text output. Dash no out is gonna hide a server certificate content. So pasting enter, and you're gonna see server certificate content from here. Certificate data, signature algorithm, and we have issuer CN, common name, wildcard, eob.amazon.aws.com. Validity, it starts from August 20, 2020, which is today, and it's gonna last for 365 days, so until 2021. Subject, common name, eob.amazon.aws.com, which is correct, and public key encryption algorithm is 24-bit, which is okay. And then this is the algorithm, and it didn't print out a public key inside the server certificate because we specified no out. So important thing is the issuer common name, subject common name, and also validity, expiration date, and it looks all good. So next step, step 2, store this TLS certificate in Kubernetes secret. So what we're gonna do is to create a secret called gateway cert AWS EOB DNS and specify TLS private key and a cert file. So we do create secret and type is TLS, and then this is the name of the secret, gateway cert AWS EOB DNS, dash key and a dash cert to specify a file path to a private key and also server certificate. And we create this secret in a dash namespace Istio system. So we're gonna copy this command and in this shell, clear first and paste and enter. Okay, so now Kubernetes secret is created. We can check this one by kubectl get secret, specify namespace, Istio system, enter. Then we should say gateway start AWS, which is this one, which was created 13 seconds ago, which is okay. So next step, step 3, reference the TLS secret we just created from Istio gateway YAML file. So we have gateway HTTPS YAML. So let's take a look here. So we are finished with 6. So inside 7, security, we have gateway HTTPS YAML, this file. All right, this is basically the same one. Okay, go back to the README. We have a gateway. Selector label is still Ingress gateway. Nothing has changed. Server configuration, we have port and incoming port to be 80 and HTTP and a host name to be eob.amazon.aws.com. We had this one before. What's changed is another new item to a server's configuration. So we have a port. Now number is 443 and a protocol is HTTPS. And host, same thing, eob.amazon.aws.com. And then we have another block called a TLS, mode simple, and a credential name. This specifies Kubernetes secret name, which is a gateway start AWS DNS, because we're using ECAS. Alright, so notice new port config here, dash port and a number 443 HTTPS, and also TLS with a secret name. So what we're gonna do is apply new configuration for gateway. So scroll down and grab this one and create a shell, enter. kubectl apply -f gateway HTTPS YAML and enter. Let's take a look in Kiali dashboard. So Istio config and then select namespace to be Istio system for sure because gateway is installed in this namespace. And select namespace to be default. Okay, so we have a booking for gateway here, this one, a second row. Click this one and then select and take a look at this YAML file. We have extra configuration here for port 443 and protocol HTTP3, and the credential name references Kubernetes secret name called gateway start AWS DNS. So it's working configuration wise. So step 4, let's test this HTTPS working or not. So let's curl HTTPS endpoint. So to do that, we're gonna curl with -- insecure, or shorthanded version is -k. As we are using self-signed certificate, this is going to be marked as insecure, so we need to pass this -- insecure, and also pass -- verbose. And endpoint would be this DNS/product page. So copy this command, paste here, enter. Alright, so scroll up, beginning of the response here. Right, so let's expand a little bit of terminal here. Okay, so we made a curl request here, and then DNS got resolved to this public IP, which is okay. And now we are making a request to 443, which is okay because this is for HTTPS. And then what's happening here is from here, there's a TLS handshake going on, back and forth between client, which is this localhost, to the server. And then this is the server certificate content. So subject, we specified common name to be EOB Amazon AWS, so which is correct. So backend server side is using the correct server certificate. That's fine. All right. And then eventually host this one, the DNS, and we do curl, and then this is the response HTTP 200, and this is a return call. So it did work actually. We can visit this URL from a browser as well. So what we're gonna do is to go to a browser. This is the HTTP, should work as well. What we are going to do is to append HTTPS : / and then this is gonna work as well. This time it's gonna show you your connection is not private. This is a warning for browser, for Chrome. Click Advanced tab, and then it says the server could not prove this is who this was because the server certificate is self-signed, but it's okay. You can say proceed to this DNS and click this one, and then this is gonna take us to booking for application. And it says it's saying warning because we are using self-signed certificate. Our server-side certificate is not signed by CA, aka certificate authority like GoDaddy or AWS or Apple. So we cannot really establish the identity of the server side, but it is okay. We are doing this for testing with self-signed certificate, right? So this is the content. It's using the correct one. So now HTTPS actually worked, which is good. So next section, 7.2, enable HTTPS, the same thing, but this time with multiple hosts. So we're going to be using SNI. SNI stands for server name invocation. using Istio Gateway. We're going to explain SNI a little bit in here, but basically, in previous section, we enabled HTTPS for this domain only. But what if we want to expose another domain? Let's say for the illustration purpose, we say testsni.com for this gateway. This is a case where we need to use SNI, aka server name invocation. So step 1, what is SNI? What is a server name invocation to begin with? So let me explain. SNI allows a single gateway load balancer proxy to host multiple TLS certificates for multiple domains on the same IP. So left hand side is typical HTTPS client, and then there's 3 different either load balancers or proxies or gateways. And each load balancer has only one server-side certificate. For site1.com, there's a TLS certificate. For site 2, second load balancer has the site2.com's TLS certificate, and so on and so forth. Whereas right-hand side, this is where there's only one load balancer or gateway or proxy, but it's gonna support HTTPS traffic for multiple domains. Let's say here, site 1, site 2, site 3. And then remember, we needed to specify common name in a TLS certificate. Like we specify this one for server-side certificates, CN common name, right? If we have different domains, we need to create another server-side TLS certificate. And if we want to bind multiple different TLS certificates to one gateway or load balancer, this is where SNI comes handy. So in previous section, we enabled HTTPS for this domain, which means gateway IP, which is the public IP like this one, binds TLS certificate with a common name with this one. Let's say we want to add another domain, testsni.com, and we want to enable HTTPS. We're going to create a second TLS certificate for this one. So now we have one-to-many relationship. This one was one-to-one, one-to-one, but this one is one-to-many relationship. This is where SNI is needed and required. So this is the case where gateway hosts multiple TLS certificates on the same IP address. So step 2, why SNI? I have explained what is SNI. In this step, I'm going to explain why. Alright? So step 1 is client is making a request, right? And the first, it does TLS handshake. We saw that from a curl. This is the handshake back and forth. It's asking server-side cert, and then server-side is asking client cert. So back and forth handshake. So this connection is a TCP level. So TLS, aka transport layer security, this is at the layer 4. This is not layer 7, which is HTTP. So what TLS, aka layer 4 means is that it doesn't know about HTTP header information, which means at this TCP connection, it doesn't know the domain name that the request wants to go to with HTTPS. So with this TLS handshake connection, first connection, server-side cannot see HTTP header host. It doesn't know, server-side doesn't know which domain's TLS certificate to return to client. So this is number 2. So this one, only one load balancer holding multiple TLS certificates for multiple domains like example.com, test.com, company.com, but doesn't know which host TLS certificate to return to client because TLS is layer 4, which doesn't have HTTP header host. So number 3, this is where SNI comes in. SNI info, which is like this attribute SNI with the domain name, it's gonna tell the server which host TLS certificate to return. So this is basically telling the server, hey, grab www.example.com's TLS certificate and give it back to me. And then therefore, in the return TLS handshake, it's gonna return certificate for www.example.com. Right? So this is why SNI is needed. TLS SSL is a transport layer, layer 4, meaning it's not application layer which contains HTTP header. And a gateway provides TLS certificate based on host attribute. But without knowing host attribute at the layer 7 level, TLS, there's no way to know about HTTP header info. It doesn't know which host TLS certificate to return to client. But with SNI info, gateway now knows about which TLS certificate to provide to client during TLS handshake. Okay, so now we understand why and what of SNI. Next is step 3. We're gonna create another TLS certificate for new domain called sni.com with a wildcard. So basically the same command here. So we're gonna copy this one, create a shell, paste, and enter. Alright, now certificate is created. As with the previous section, we can check the content of a server-side certificate by this command and scroll up and make sure to check common name is sni.com for illustration purpose. So step 4, same thing. We're gonna create a secret and then store these private key and the server-side certificate to a secret. So grab this one, copy, paste, enter. Now new secret is created. Let's check that. Create a shell and then kubectl get secret namespace stl system, enter. And it should show us gateway start AWS which we created in the first time, and then this is the S9 DNS. This is the one that we created 14 seconds ago. Lastly, step 5, we're gonna reference this second TLS secret from Istio gateway YAML. So remember earlier we added a new port configuration for 443 in eobamazon.com with a TLS for the first secret. Now this is the new server config for sni.com. This is where gateway supports multiple domains with multiple HTTPS configuration. So port number is going to be still 443. Name, this shouldn't conflict with this HTTPS, so you can just add some arbitrary name that doesn't conflict with the existing one like HTTPS. So just make it meaningful, like HTTPS-SNI must be unique. Protocol is HTTPS. Host would be this one. Host should be the same one as the common name specified in the server-side certificate. So which is this one, wildcard sni.com, and TLS credential name specifies secret name. So this is the newly added section, and this is available gateway HTTPS SNI YAML. So what we're gonna do is take a look here, gateway HTTPS SNI, right? This is the configuration. This is the part that we added. So we're gonna apply this one, copy this command, copy, create shell, paste, kubectl apply, gateway HTTPS SNI YAML, enter. Worked. You can check if config is correct from a Chiari dashboard. So it's the same exercise. Istio config, and then we should see booking for gateway. Then nothing showing error here. If there's an error, then there's a red highlighted color at the line with a syntax error. But because this is the correct one, it's okay. And here configuration it says green, valid. So configuration worked. We've seen this one, looks good. And finally, a gateway and a virtual service need to be created and binded for the configuration to work. We have edited gateway to allow incoming requests to this SNI, but we haven't configured a backend virtual service to accept it and then route traffic to backend service yet. So we need to add *sni.com to virtual service host. So in this virtual service HTTP bin SNI YAML, we have a virtual service and we have a host section with a list of hosts. We already have eobamazon.com and we have a HTTP bin. And then next we're gonna have sni.com with asterisk. This is where we want to add. So we're gonna take a look at this virtual service HTTP SNI YAML file in this folder. So that'll be not the folder 6 but 7, virtual service. So virtual service HTTP SNI YAML. Alright, so here, this one we added another domain name for this HTTP to route to. So we have added this one. So we're gonna apply this. So grab this one, kubectl apply -f virtual service HTTP SNI YAML. Paste, enter. Okay, so it worked. That's good. Also, after adding sni.com host in the list of hosts here in a virtual service, we also want to note that in an HTTP block, we have a match condition for slash and a /IP and /headers. All of these HTTP path requests should be routed to destination HTTP bin default service cluster local at port 80. So first we're gonna deploy HTTP bin pod, and then after that we're gonna expose HTTP bin pod using a service, and then open the service port as 80. And then all the traffic to slash and a /IP and headers are going to be routed to HTTP bin, where it returns a HTTP header request. So we are adding a new path, and also we are adding a new pod. So notice new item in the host list, and then we deploy this one. And after, we're gonna deploy HTTP bin. So pod HTTP bin YAML is found here, pod HTTP bin YAML, right? So take a look at the pod HTTP bin YAML, which is this one. Basically, kind is pod, and a container image is called HTTP bin. Name HTTP bin. All right. So we're gonna deploy this one. So copy this command and clear, paste, and enter. And a new pod will be created. Here it's gonna show up as HTTP bin. This one, good. And next we're gonna expose this pod using a service at the port 80. So paste expose pod HTTP bin port 80, enter. Right? It's expose service should appear here in a service after 2 seconds. Right? So yeah, HTTP bin port 80 type class IP, which is okay, just an internal one. So to test HTTPS for SNI.com, we have several tests. So before SNI, first make sure there is no regression, meaning that we don't want to break anything. So what we're going to do is to make a curl request to product page. This should work. We have already enabled HTTPS for product page using Amazon DNS, Amazon EOB's DNS. Okay, so this worked, right? HTTPS, and then we have HTTP file, HTML file. So we have 200. We need to take a look at which domain and which certificate is used. So the certificate used for this one is eob.amazon.com, which is correct, and then 200, which is okay. Now, this is a successful output. Notice that server certificate specifies common name, which is this one. This is where we know that which certificate is used. Okay, now after SNI, we are going to access gateway, in our case, AWS EOB public DNS, but with *sni.com domain, so that gateway would return TLS certificate for *sni.com instead of existing EOB Amazon AWS.com TLS certificate. So we're going to make a curl request like these two. Both of these work, but there's a warning. I have spent more than actually 1 day to debug this. So here, let's take a look at this curl command. This is a simplified version. So what we're gonna do is that we are going to set destination URL of curl command to be https://test.sni.com and secure ingress port. This is the shell variable we define here, and then /headers. And the /headers is defined in this virtual service. In here, /headers is under the match condition in the URI, and then if HTTP path contains slash or /IP or /headers, then request is going to be routed to HTTP bin service at the port 80. So what we're going to do is to make a request with a destination testsni.com, because this is the one that is included in TLS certificate's common name, and then /headers. But we don't own this sni.com, so this is not publicly accessible. But we need to send HTTP host header to be sni.com. How to do that without owning actual sni.com is using -- resolve argument. So here with the curl, we can pass resolve test sni.com security ingress port, which is exactly the same as this one. So basically how to read this resolve argument is first two values separated by column, test sni.com secure ingress port, which is this one, is gonna be replaced by the latter part. And what is the latter part? This is where I spent a lot of time to make it work. So if you go to Istio documentation page and follow their guide, then they're gonna use this ingress host variable with this JSON path for ingress host name. This works on Istio documentation page because they are not using AWS's load balancer or GCP's load balancer, in which case this host name is gonna be actual DNS name. Whereas on Istio webpage, they are using probably a local version of Kubernetes cluster, so host name is going to actually return IP address. And this -- resolve is going to only work if replacement part, the latter part is IP address, because the resolve means that let's resolve this DNS part with actual IP address. But if you're using public cloud provider like AWS or GCP, then this host name, which is DNS, if you pass DNS, then you cannot do that. So let's try with anti-pattern. So we have secure ingress port is 443 and export ingress host is gonna be actual DNS. Let's echo ingress host. So paste, enter. Ingress host is actually DNS. This is not IP address. If you wanna get public IP which this DNS name resolves to, then you can use host command and paste this domain name and enter. Then it's gonna resolve to 2 different IP addresses. These are for higher availabilities. If we are going to do this curl with -- resolve with first part, and then after, this is the anti-pattern I want to show you because I came across this error. So if I want to make these first 2 parts resolve to just this ingress host, which is this DNS, this wouldn't work because this first part, this part cannot be resolved to another DNS name. So see, it shows us error saying could not resolve testsni.com. The reason being here, could not resolve host testsni.com. This is because, first of all, this testsni.com is not publicly accessible. We don't own this domain. So this -- resolve argument should replace this unaccessible host with public DNS IP address. But we passed this DNS, which isn't gonna work. So we should be passing this IP part. So that's why we have subshell with host. So what we are going to do is do host and a DNS, and it's gonna return 2, right? So what we're gonna do is host and echo ingress host, which is gonna return the same thing. And after that, we're gonna do tail and get the last element, and then we're gonna get 4th column, which is IP address, because this is the 1st, 2nd, 3rd, 4th. So that's what we need to do. So see here, this one, and then pipe tail and a -1 to get the last comment, last element, and do pipe again and do org command, org, and then do print and then 4th column. So this is the syntax. It's gonna print out this IP. So we want to resolve this first part with this public IP. That's why we need to use this subshell and a host and then this pipe command. With this is going to work. So create a shell first, paste, and enter. Now, tada, it's working. So it returned 200. And let's take a look at the certificate because this is important. So this is not working because it's not public IP, just DNS. So I put the warning at the top here, warning, if ingress host resolve to DNS host, not IP, then passing -- resolve to resolve this part with this DNS doesn't work. You need to resolve this ingress host DNS to IP first by replacing it with host echo blah blah blah. This is because of curl command. So if you do curl --help, and you have a -- resolve over here, -- resolve host post address, host port and address, false resolve of host port with address. So exactly the same one. So host port with address, not their DNS. So this is the only way it'll work. So I'm gonna make another curl command, and then we are interested in, all right, from here. So obviously this curl request succeeded. Hostname testsni.com was found in DNS cache and then got resolved to this IP because we did resolve with IP, and then connected to load balancer's IP. TLS handshake is happening, and then what I want you to take a look here is TLS certificates content. So now common name is sni.com. So gateway is using right TLS certificate for sni.com because we passed this test sni.com. Okay, so that's successful. And eventually return 200. This is a response from HTTP bin/headers. So HTTP bin/headers is supposed to return HTTP header content, so we can see what attributes are passed as HTTP request. Alright, so this is working. So SNI is working. I just wanted to leave non-working curl examples. So if you pass sni.com, wouldn't work because SNI is not *sni.com. So I can show you by demonstrating here. Scroll down here and pass this. It didn't work. So first create a shell, paste, enter. Here it says error, SSL error, syscall in connection to sni.com. So this doesn't work. Alright, here this doesn't work either because I've said ingress host DNS should be replaced by IP. So right now here it doesn't pass IP, it's just passing the pure DNS. So you need to do a host of this one and then trim out and get IP. So this doesn't work. Also this one, the third one is not working because this domain destination is not wildcardsni.com, so this doesn't work either. Okay, anyways, so this is the how you can configure and verify SNI. This was pretty difficult for me to make it work because Istio documentation, in that case, the guide wasn't using public cloud's load balancer, therefore hostname actually return IP address, whereas my case I was using AWS load balancer, so hostname actually returned a DNS, not the IP, and that I didn't notice this part, hostname. So if you're using public cloud like GKE or EKS, this just passing this ingress host, this is what you can find on the Istio documentation page. But if you just keep using ingress host, this doesn't work. So you need to add and you need to resolve this DNS to a public IP address. Next section, 7.3, we are going to verify mutual TLS among applications inside Istio service mesh. So I've already mentioned in chapter 1, but by default, if you install Istio version 1.6 and 7 or even 1.5, all the applications inside Istio service mesh are mutual TLS, meaning that connections from, let's say, from this product page pod to, let's say, review service going this way, the connection is TLS enabled because of Envoy sidecar proxy. So this section is about how to verify that connection is actually mutual TLS. So here, all traffic between workloads with proxies use mutual TLS without you doing anything. And when using mutual TLS, the Istio sidecar proxy injects the X-forwarded client cert header to the upstream request to the backend. The header's presence is evidence that mutual TLS is used. So let's make a curl request from curl pod to HTTP bin, which is here. So we're going to create new curl. So from here, copy this command, run curl -- dry run -o YAML, and it's going to save this YAML content to pod curl YAML, which is already here using a curl image, and basically it's going to sleep infinite. Okay, so what we're going to do is to just do this, kubectl apply f pod curl YAML, and the curl pod is going to appear here 2 seconds after. Okay, so curl is appearing, and then next we're gonna get a shell inside this curl container, and then what we're gonna do is to curl http bin /headers. http bin is the service name of http bin, and then we're gonna hit headers http path, and then we're gonna look for X-forwarded client cert by using grep command. So what we're gonna do is kubectl exec -it curl sh, and we are inside the curl container, and if we do curl http bin headers, it's going to return a HTTP header sent to this HTTP bin. And inside here, the last one, X-forwarded client cert. This is the evidence that mutual TLS is enabled because Istio Envoy proxy is going to add this one for mutual TLS enabled connections. The fact that X-forwarded client cert is injected by Istio sidecar proxy inside the curl pod when making a request to HTTP bin pod, which is what we did. We made a request from curl to HTTP bin, but any incoming or outgoing requests are intercepted by sidecar because curl had 2 out of 2, meaning that Istio sidecar envoy proxy is also inside the pod. So request outgoing request was intercepted and new header attribute was added by Istio envoy sidecar proxy. So because of this, mutual TLS is enabled. We verify that. Next, 7.4, enable strict mutual TLS in mesh globally, meaning all namespaces. What I mean by strict one is that while Istio automatically upgrades all traffic between proxies and the workloads to mutual TLS between, workloads can still receive plain text traffic from some other pods. To prevent non-mutual TLS connection for the whole mesh, set a mesh-wide peer authentication policy to set mutual TLS mode to strict. So what I mean by this one is that there are 2 different modes of mutual TLS. Default is permissive mode, meaning that everything from a pod within a namespace where Istio is enabled, all the outgoing is going to be mutual TLS. But if request is coming from a pod inside a namespace where Istio is not enabled, then there's no sidecar injected to the pod, and therefore that pod is going to make plain HTTP request. So strict mode is going to reject any plain text traffic. So that's what we are going to do. Before, let's verify. So this is the before strict mode. This is a default. You can send non-mutual TLS traffic from curl pod in different namespace to HTTP bin pod in default namespace where Istio is enabled. So what we're gonna do is first create a new namespace without enabling Istio sidecar injection. So we're gonna create non-Istio namespace, and we are not gonna enable sidecar injection, okay? So first we're gonna get out of this shell, curl container, clear, paste. We're gonna create a non-Istio. This one we don't enable Istio sidecar injection. And then from here we are going to create curl pod. So we have another one, pod curl non-Istio. Only difference is that namespace is non-Istio. Everything else is the same. So we are creating curl pod but in non-Istio namespace. So let's check that. kubectl get pod namespace non-Istio. What you are going to see is that the ready column is going to be 1 out of 1 because there's no sidecar injection for Envoy proxy, which is okay. So any request from this one to, let's say, this HTTP bin is going to be plain text because Envoy proxy doesn't exist, and therefore the connection is not going to be mutual TLS enabled. So what we're going to do is that we have verified that pod is created with 1 out of 1. We are going to get a shell inside this pod inside, and from inside we're gonna make a curl request to HTTP bin in Istio enabled default namespace. So we're gonna do is grab this command, paste, enter, exec into curl pod in namespace non-Istio. So inside this curl pods curl container, we are inside. Now what we are going to do is to do curl, but this time not just HTTP bin, but we need to append namespace .default because this one is inside non-Istio. So without explicitly specifying namespace here, it's gonna send request to HTTP bin in this namespace which doesn't exist yet. So we're gonna do curl HTTP bin in the default namespace / headers. See, we don't see the exported header because there's no Istio Envoy proxy. So this is just a plain text. At least the plain text connection is still enabled for this HTTP bin. So what we're gonna do with the strict mode is that we're gonna disable HTTP plain text connection from this one to this one. To do that, we're gonna follow this section after strict mode. So first we're gonna create a new resource called peer authentication. This is a peer authentication strict mutual TLS global YAML file. Basically, this is a really simple YAML file. Spec contains mutual TLS. Mode by default is permissive. We're gonna set it to strict. So it's a peer authentication strict mutual TLS global YAML. There's already a file in this folder. So peer authentication strict mutual TLS. File we're gonna use is a TLS global. So this one. So we're gonna just set it to a strict. Alright. The namespace is gonna be Istio system. This is for global. The root namespace for Istio is Istio system. Root namespace for Kubernetes is a kube system. So if you want to set it globally, meaning all the namespaces, then we're gonna select Istio namespace. So now we commented out this namespace default. We're gonna set it to a root, which is gonna be applied to global. So coming back here, we're gonna grab this command, kubectl. So we're gonna first exit out from shell, clear shell, and then paste. Apply peer authentication, mutual TLS, okay? Grab this command and then paste and then enter. So this apply peer authentication strict mutual TLS global. Now it's created. So now try to send a non-mutual TLS traffic, which means curl from non-Istio namespace to HTTP bin in default namespace, just like we did earlier. This time it's going to fail. So first, get a shell inside the curl container in non-Istio namespace. We are inside. Let's make a curl request to default namespace HTTP bin / headers with dash bubbles. And now we see closing connection, failure, connection reset by peer. So we didn't receive 200. So receive failure, connection reset by peer. So this doesn't work. This is expected. Connection is refused by this one because now mutual TLS is in strict mode. Alright, this applies to all the namespaces. This is global one. So we just verify that. So next section, section 7.5, we're gonna enable strict mutual TLS in mesh per namespace. So here in this peer authentication, we have namespace default next time as opposed to Istio system. And then what's gonna happen is that curl in this non-Istio namespace, which is this one is going to request is gonna be rejected because we specify that we want to enforce strict mutual TLS in this default namespace only, and therefore this request is going to be still rejected because of insecure plane. Alright, let's do that. It's a little small change. So what we are going to do is to first disable global peer authentication config we just did in the previous section, because we first need to delete that one. So to do that, we are going to do delete peer authentication default dash name is your system, paste and enter, and then this default one is deleted, so global one is gone. So next we are going to do is to do mutual TLS default namespace only. So before, this namespace was Istio system, the root namespace. Now it's gonna specify only default one. Everything else is still the same. Alright, so we're gonna grab this command and clear shell, paste, apply peer authentication, mutual TLS, strict mode for default namespace, and then enter. Alright, it's created. So let's verify no mutual TLS request is still blocked. Nothing's gonna change because this curl container is still in non-Istio, and this one is also in the default one. Okay, and then let's make a curl request HB bin receive failure. So that is expected. But let's say we are going to create HTTP bin in new Istio enabled namespace. So what we're gonna test is that Istio enabled namespace, any outgoing request is gonna be mutual TLS enabled. So in different namespace HB bin, this plain text connection to other namespace HB bin is not gonna be blocked because strict mutual TLS mode is not enforced in this namespace. It's only enforced in this default namespace, but not in this Istio enabled namespace. So we're gonna create Istio enabled namespace here. So first exit out from container, clear, paste, create namespace Istio enabled, and then we're gonna enable Istio sidecar injection. So that is this one, label namespace Istio enabled. This is a namespace, and then we're gonna add the label Istio injection equal enabled, enter. Okay, one more time, entire command and enter. Okay, so now this namespace Istio injection is enabled. And what we are going to do is we are going to create HTTP bin pod in this Istio enabled namespace, which doesn't have strict mutual TLS mode enabled. Okay, so what we're gonna do is create this one, and this time namespace Istio enabled. So paste, enter, create it. Let's check that. kubectl get pod namespace Istio enabled, enter. Should be HB bin, good. And then it's sidecar injection enabled, that's why it's 2 out of 2. Alright, so now we are going to expose this pod with a service with expose pod HB bin and dash name Istio enabled, enter. There should be service created, and then we are going back to get a shell into curl container in non-Istio and make a request with a plain text. So we are inside the shell, alright, and we are going to make request to HB bin, but this time Istio enabled namespace. In this namespace, remember, strict mutual TLS is not enabled. Therefore, it's gonna still accept plain text request. So see, it returned 200 with HB header content because mutual TLS with a strict mode is not enabled. However, if we do with a default namespace like this one, default namespace, it's not gonna work because strict mode is enabled only for this namespace. So we have successfully verified that strict mutual TLS mode is enabled per namespace. It works for Istio enabled, but not for default. That's all. Alright, so next section, 7.6, we're gonna enable strict mutual TLS in mesh per workload in a namespace. So we're gonna have more granular, fine-grained control over which pod is gonna have this strict mode enabled. Not just all the pods in a namespace, but just specific pods we're gonna enable a strict mode. So we can do workload specific peer authentication policy as opposed to namespace wide or mesh wide. So as you have probably already noticed from the 2 previous sections, we have been narrowing down the scope of strict mutual TLS mode one by one. We started with a root global mesh. In the previous section, we narrowed it down to just a default namespace. And in this section, we're gonna be narrowing down even more to just a specific workload or pods in the namespace. So before strict mode per workload, you cannot send non-mutual TLS traffic from curl to HTTP bin pod in default namespace, this one, because it was namespace wide mutual TLS in strict mode. So that's what we already did, which is here to a default namespace, it couldn't do it. After strict mode per workload, first we want to disable peer authentication config we just created in default namespace because this was a namespace wide one. So we want to start with a clean slate. So we're gonna exit out from container, create the shell, paste, and delete peer authentication in the default. From here, we're gonna be using peer authentication strict mutual TLS HTTP bin. We're gonna configure strict mutual TLS for all the incoming requested pod with a label app HTTP bin only in default namespace. So what has changed in peer authentication is namespace is gonna be still the default, but we added this selector block where we define key value pair of label. So all the pods, any pods with this label run HTTP bin, then strict mutual TLS is going to be enabled, meaning that this one is going to still block plain text. However, all the other pods in this default namespace can still accept a plain text HTTP request. Alright, so let's do that. But this alone doesn't work with workload specific strict mutual TLS mode. We also need to create a destination rule because Istio cannot aggregate workload level policies for outbound mutual TLS traffic to a service. So what we need to do is to create a destination rule. Remember, destination rule is added after virtual service. And then we're gonna create name HTTP bin. Host is gonna be HTTP bin default. So this specify outgoing request to which host that config will be applied to. So we have traffic policy TLS mode Istio mutual. This is basically enforcing strict mutual TLS for outgoing requests to HTTP bin in default namespace. This alone doesn't work because there are a lot of requests outgoing to this HTTP bin. So we need to enforce, kind of bundle together outgoing requests with this destination rule and then specify host and traffic policy to be Istio mutual. So let's apply these two YAML files. So grab these two commands and copy and then paste. Okay, the configuration completed. So verify that non-mutual TLS plain text connection to HTTP bin in default namespace is still blocked, but request to product page in default namespace is not. So all others can still accept HTTP plain request. So again, get a shell inside a curl container in non-Istio, and then let's make a curl request to HTTP bin in default. This is gonna be blocked. Yes, it's gonna be still blocked. But if we do curl to product page in default one, this should work. Yes, it's 200, right? This is because we enabled strict mutual TLS mode for HTTP bin pod only. Alright, so this just verified workload specific strict mutual TLS in the mesh. Right, lastly, section 7.7, let's enable HTTP redirect to HTTPS. This is gonna be easy. So in this gateway HTTPS SNI host, so in this gateway HTTPS SNI HTTPS redirect YAML has a configuration for redirect port 80 to port 443. So under server's configuration, we have another item called port, and port 80, we used to have this one, and the host is gonna be this one, but we have TLS HTTPS redirect true. So this is the one that is added to the existing one. So let's take a look in the Kiali Istio config, and remember we have booking for gateway and also virtual service, but gateway defines incoming port. So we have incoming port HTTP and 80. We want to add TLS configuration like this one under HTTP, and then we want to add HTTPS redirect true. So we already have this YAML file, gateway HTTPS. So it's gonna be gateway HTTPS SNI and HTTPS redirect. So we have port configuration for port 80, but this time we added TLS HTTP redirect true. So we're gonna use this one. So we're gonna grab a command here and exit out from the container, clear the shell, paste, and then enter. Okay, so configured. Let's reload this gateway. Now we have TLS HTTPS redirect true. Okay, so let's test this out. So we're gonna make a curl request to load balancers DNS and headers. Remember we had a virtual service for headers, and for all the requests, the header is gonna be routed to HTTP bin. So we have HTTP header as a response. But this time we are making a request to HTTP port 80. And we should receive HTTP 301 moved permanently because now HTTP is getting redirected to HTTPS. How to follow this one is basically you can just do dash, it's gonna do follow. Okay, Okay, so one more time, clear shell, enter with -L this time. And now it's redirecting the following to, first we got 301. Second request is going to HTTPS, right? So we are following the redirect and then we do TLS handshake, but it's complaining because it's insecure one, so we need to pass -K insecure, right? Now that's TLS handshake. And now it does use TLS certificate for eobamazon.com, which is fine. And after that, it returns HTTP 200. And this is the HTTP return from HTTP bin/headers endpoint, which is just a header. So we just verified that redirect works, and we also followed and got response from HTTPS endpoint by passing -L and -K. Alright, that's it for this chapter about HTTPS, basically securing traffic in transit. So chapter 8, we're going to be talking about authentication and authorization using JOT, JSON Web Token. Section 8.1, we're going to enable end-user authentication with the JSON Web Token for entire gateway using request authentication and authorization policy custom resources for Istio. So we're going to be dealing with the two different new custom resources for Istio, and then we're going to explain that. Okay, so let's take a look at this diagram. So we have Istio Ingress Gateway and also new request authentication and authorization policy. And then we have load balancer, Ingress Gateway service, and gateway pod, within which there's a standalone Envoy proxy running inside here for layer 7 load balancing. And then we have virtual services here. So what we're going to do is to create request authentication YAML, where we're going to define Ingress Gateway by label here, Istio Ingress Gateway, which references this one. And then we're going to add JOT rules with issuer and JSON Web Tokens URI. So what this YAML file is going to do is to require user to provide a valid JSON Web Token when they are making a request through gateway and then to the backend virtual services and also pod. So in this example, this is a case where authorized user make HTTP request. Inside the HTTP header, we have authorization bearer token, which is this one, and this is a valid one. So green arrow from outside with VPC, go through gateway, and then here, because of this policy, and because JSON Web Token gets validated, the request gets through this gateway and eventually hit the backend of the viewed service. Whereas unauthorized user case, where HTTP header doesn't include authorization bearer token, the request goes through Internet Gateway load balancer and eventually hit a gateway here. And at this point, there's another custom resource called authorization policy created. And here you see action deny. So this is a deny rule. And if request principals, which should be existent if there is a valid JSON Web Token. So in this case, this is a valid JSON Web Token, and therefore you can find this request principals in a header. But if no valid JSON Web Token is provided here in this case, then we are not gonna see request principals. So this is an if condition. If no request principals are provided, then the request should be denied. And this is applied at the Ingress Gateway level here. So therefore, request without authorization token is gonna be rejected, and eventually 401 HTTP unauthorized error code is going to be returned. So this is what we're going to do. Alright, so step 1, we're going to create Istio request authentication and authorization policy. So we have two YAML files here. First one is request authentication YAML. And we are going to add a request authentication policy that requires end user JOT for the Ingress Gateway. So we have a kind request authentication, namespace Istio system. That means this rule applies to all the namespaces inside the Istio service mesh because this is the root namespace for Istio. And under the spec section, we have a selector and a match labels and a key value pair. So this is the Istio Ingress Gateway. So this is going to reference Ingress Gateway pod created when you install the Istio. And then beneath that, we have JOT rules and we have issuer and a JOT's URI. So this contains a valid JSON Web Token. And then we have another YAML file called authorization policy YAML. Here we are going to add authorization policy. This is authorization, whereas the previous one was just authentication. With this policy, with a rule specifying a deny action for request without request principals, which are available only when valid JSON Web Tokens are provided. So I have already explained, but here there's a rules from source. If source does not include requested principals, which usually comes with a valid JSON Web Token, and then you should deny this request. So basically this is saying explicitly deny any request without request principals. So any invalid JSON Web Token are going to be rejected, right? So let's copy these two commands and paste in and then enter. So two resources are created. So you can go to k8s to check that. So open k8s dashboard and go to Istio config, and under here in this table we should see new custom resources called authorization policy and request authentication. All right, so click on this request authentication JOT example. We have defined JOT rules, which is okay. And also let's take a look at authorization policy front-end ingress. We defined deny action for any request without request principals, so it looks okay. Alright, so next what we're gonna do is to test JSON Web Token authentication working. So we are trying to access HTTP headers/headers endpoint without passing JSON Web Token, and this should fail with HTTP 403 forbidden. The reason being, we have introduced new custom resources like request authentication and especially this authorization policy where it's gonna deny any request without valid JSON Web Token. This is applied at the root namespace Istio system. Inside any namespaces in the Istio service mesh, we now need to pass JSON Web Token so that request gets authenticated and authorized. So let's grab this command, curl ingress host headers -b. So ingress host shell variable should be already exported from the last chapter. And paste and enter. Alright, right now we see 403 forbidden, and this is expected. So next, we are trying with passing invalid token. This is like a random web token with authorization bearer in a header. So we're gonna use curl with a -- header, authorization bearer with a random token here. This is an invalid one. And try to hit the same endpoint /headers. So we are going to copy this one and clear shell, paste, and enter. This is gonna also result in 400 error code. This time it's 401 unauthorized. So this is because JSON Web Token is not in the form of a header payload signature. This is because this is invalid. Next, we are going to try with passing a valid token in authorization bearer header, and this will return 200. So what we are going to do here is this command first. We are going to export valid JSON Web Token into this token shell variable. So we're going to copy these two, and this is just for a sample demonstration purpose. So enter, and then second line echo shell variable token. It's going to print out the content of a valid JSON Web Token. This is a sample one. So we are going to use this one. So next we are going to copy this command with -- header argument and a token. This is going to be taken from this. This is a valid one. This is available publicly on the internet. This is for sample use case only though. And then we're going to make request again. Enter. Alright. So right now we see 301 moved permanently. This is because at the end of last chapter, we enabled HTTP redirect to HTTPS. So if we are going to do with this one, with -L to follow the redirect, we are going to see insecure warning. So we are going to do is to pass -K, which is -- insecure, and enter. And then eventually it's going to redirect HTTP to HTTPS, and then finally it returns 200. And then this is the header content returned from this HTTP bin /headers HTTP path endpoint. So now with a valid JSON Web Token, everything worked right now. So next section 8.2, we're gonna enable end user authentication with a JSON Web Token per path. So what we're gonna do here is to build on top of what we have already done in the previous section. Basically what we're gonna do is to narrow down the scope of this authorization policy under a specific path as opposed to all the endpoints. So here, what's changed here is authorization policy. We also have deny rule, but also there's a new section called to operation path and /headers. In this way, we're gonna only require valid JSON Web Token for the /headers endpoint. All other endpoints don't require JSON Web Token. So in this diagram, authorized user is still going to send a valid JSON Web Token, but this time destination is /headers. And then because the JSON Web Token is valid, it gets through this ingress gateway and it's going to reach backend reviews. Whereas unauthorized users, without passing valid JSON Web Token for destination/headers, is going to still get 401 unauthorized. What's different from previous section is that normal user without passing valid JSON Web Token can still access other endpoints like /IP. So I'm going to demonstrate that as well. So we have authorization policy, but this time it's going to only require the token for this /headers. So it says deny if invalid JSON Web Token is passed for this endpoint headers. All other endpoints doesn't matter if they're valid or invalid. So what you're going to use is this authorization policy /HTTP bin YAML file. This is also in chapter 8 folder. So take a look here. This is 7, 8, and the name is called authorization policy HTTP bin path. So which is this one. All right. So nothing has changed except the rules section, and then from we already have that from previous section, and then we added 2 operation. So if destination is toward /headers, then deny. It's coming from a request with no valid JSON Web Token. Alright, so let's grab this command here and then paste in and enter. Okay, so now new configuration is applied. Let's check that from Kiali. So we are looking at authorization policy, so this one, and we have new section. So let's reload this configuration. Alright, so go to Istio config, and then we selected both default and Istio system. So this time, authorization policy got created under default namespace and called allow path. We already had previous one called authorization policy front ingress. This one applies to global namespace. So this applies globally among all the namespaces in Istio service mesh, but we have just created a new one in a default namespace called allow path. This applies only to a default namespace, and we added this section. So /headers in the namespace default, then it'll be denied without valid JSON Web Token. Okay, so how to test /headers? Okay, so we're gonna test headers fail without a valid JSON Web Token. So this section. So we're going to do is to curl this /headers endpoint without passing valid JSON Web Token. This should fail. Okay, and enter. For 3 forbidden, this is expected. The last message says RBAC access denied. RBAC stands for role-based access control. Now we are going to pass valid JSON Web Token. Copy this command, clear, and paste, enter. Now it says 301 moved permanently. The same exercise. Add -L to follow and -K for insecure. And eventually this is going to return 200, 200 with HTTP header content returned from HTTP bin /headers endpoint. Next, we are going to test /IP endpoint, and this should succeed without passing a valid JSON Web Token because we have enabled this authorization policy only for /headers. So this should still work without passing valid JSON Web Token. So clear shell, paste this time /IP of this HTTP bin. This is already exposed by a virtual service. So enter. This should return source IP address. So now it says 403 forbidden. This is probably because there's a global authorization policy requiring valid JSON Web Token. So what we need to do is to delete a global one first. Alright, so to do that, we are going to see clear kubectl get authorization policy in a default namespace, allow path, which is okay, namespace Istio system, and then we have this one global requiring all the requests with valid JSON Web Token. So what we're gonna do is to delete kubectl delete authorization policy front end ingress -name Istio system. Enter. Alright, delete it. And let's try with /IP endpoint. This time it's 301, so it's gonna do same -L -K. It should return a source IP. So now it should work. This time we didn't pass any valid JSON Web Token, but only thing we needed to do is to disable the global one, which we created in section 8.1. So section 8.1, we allow this one, like we allowed all the requests to be supplied with a valid JSON Web Token. This was hindering us to send requests to /IP without valid JSON Web Token. History. And so what we needed to do is to just delete this global one in the beginning. First, delete global authorization policy applied. Alright, so make sure to delete this one first, and then after make a curl request. So section 8.3, we're gonna enable end user authentication with a JSON Web Token per host and a path. In the previous section, we have specified the path for /headers. This time, we're gonna be adding another condition. In this case, we're gonna be adding another host called testsni.com. So take a look at this YAML file in authorization policy HB path host YAML file. Kind is authorization policy, and selector is ingress gateway. So this rule is gonna apply to ingress gateway in Istio system. And the action is deny. So deny if there's no valid JSON Web Token. This doesn't change. Hasn't changed from previous section. And to operation, we had /headers in previous section. Now we have a new line called host testsni.com. And there's a slight subtleties here. So we could have host testsni.com under operation list, or we could have another list called operation with host testsni.com. In this case, this would be AND condition. So condition is going to be evaluated like this. If domain is testsni.com and HTTP path is /headers, then this is going to apply. And in that case, we need a valid JSON Web Token, or else we're going to deny the request. Whereas if we uncomment out this section, this is going to be OR condition, meaning that first condition is this /headers, or host is testsni.com, and it doesn't matter if HTTP path is headers or not. So this is gonna be either domain name is testsni.com or path is headers. So this is or. We're gonna be just doing an AND condition. So host is testsni and HTTP path is headers. So we're gonna do is to first delete previous authorization policy created in a previous section. So we're gonna do this, copy and paste. I've already done that earlier, so we are not gonna find this one. And then after, we are going to apply this one, okay? And go to Istio config and select both namespaces, and we have authorization policy, and we have here says host name no matching entry in a service entry, but do not worry about it. It doesn't affect us from testing. So what we're going to do is to test headers endpoint with sni.com. So this is the AND condition. If we want to hit test sni.com /headers, but without valid JSON Web Token, it should be receiving errors. So what we're gonna do is copy this command. Basically, current destination host is testsni.com with 443, and we're gonna use --resolve argument to resolve first these two parts with public IP of public DNS load balancer. So what we're gonna do is paste this command and enter. Alright, we now are getting 403. If you look at the server certificate content, then you know that correct TLS certificate is selected based on this domain name that we use. So the load balancer or gateway is using sni.com TLS certificate. So host is actually testsni.com because of a destination domain we selected here. And we are receiving RBAC access denied. This is expected. Next, we are going to test /headers with sni.com with valid JSON Web Token. So what's changed is we are passing --header with authorization bearer with valid token. This is already exported as a shell variable earlier. So we're going to pass this one on top of destination domain to be testsni, and we are going to be resolving this one with a public IP of public load balancer DNS. So we are going to copy this command, clear shell first, paste and enter. Alright, so now we see 200. Okay, so it's successful. Server certificate is still SNI and it's 200 because we passed valid JSON Web Token. So we see HTTP header request content are these. And you can see here authorization bearer, we have a valid JSON Web Token passed as part of the HTTP request. Alright, so next we are going to test /headers with non-sni.com domain. So we're gonna just use AmazonAWS.com. This is a public DNS about load balancer without passing valid JSON Web Token. This should work because when we created this authorization policy, we configured it in a way that these conditions are to be used as AND condition. So if this and that, so if we are not using this domain, for example, if you're using public DNS of an AWS load balancer, which is not same as this one, then this AND condition is going to be false. In that case, the request shouldn't be rejected. So what we're going to do is to scroll down and copy this command. Basically, this ingress host domain name is going to be this EOB Amazon AWS.com. And then we're going to hit headers. So paste and enter. Okay, so right now we got another 200. Take a look at the server certificate common name. There's another one, tier certificate for this one. So this correct one is used by gateway based on this domain name in the HTTP header. So you see host is this one, AOB Amazon AWS.com. Because this is not testsni.com specified in authorization policy and condition return false, therefore this didn't get rejected without valid JSON Web Token. Next section, section 8.4, we're going to enable authorization using HTTP header attribute. So what's changed is this block. So basically we are adding more and more conditions for when we want to enable authorization with JSON Web Token. So at this point we have AND condition and when HTTP header contains X token as a key and a value as admin. So if that's the case, these are all AND condition, then it requires valid JSON Web Token. So this is kind of a useful when you want to expose some test endpoint, like let's say application version 2 for a domain with specific header attribute. Let's say could be like username to be tester. Only then you can access that endpoint using valid JSON Web Token. So in a way, this is how you can do authentication and authorization. Without that, normal users cannot access this new version 1 endpoint, version 2 endpoint. So we are going to apply this YAML file. So copy this one. So first delete a previous authorization policy created in the previous section. So clear the shell, enter, delete file authorization policy, HTTP path host. Got deleted. So go to istio config. Now there's no authorization policy. And then grab this command and paste and enter. Right, so YAML file doesn't exist. Right, so again, paste, enter. Now configured, go to istio config, refresh button, and now I see deny header in istio system, and then we have host. This host has no matching entry in a service registry. This we've seen that in the previous section, so don't worry about it, just keep moving on. So we're gonna test headers with sni.com with a valid JSON Web Token, but it's gonna fail without passing this X token admin value. So let's try that. This used to work in a previous section, but because we added a new condition for this header attribute, this should fail, right? So we're gonna do a header attribute with valid JSON Web Token and domain to be tested SNI. So this is the AND condition. This and headers used to work. So paste, enter, and right now this should fail 403. RBAC access denied. So server certificate is sni.com, host is sni, and endpoint is headers, but because it's complaining because we needed to pass this one. So next we're gonna try with a slash header same endpoint with the same domain with a valid JSON Web Token, but value of X token to be non-valid one. So we are passing test, whereas in the configuration it requires value to be admin. If value is not admin, then deny action kicks in. So because we are passing non-admin value, this should fail as well. So copy here. The way we are passing header attribute with X token test is here. -- header for curl command with X token as a key, space, and value as test. So clear shell, paste, enter. Alright, so again 403. RBAC access denied. This is expected. Here we have X token test. This is supposed to be admin. So this is the successful case. We're gonna pass header X token with admin. This should succeed finally. Alright, so copy this command, clear shell first, paste. Here X token is admin, enter. Alright, so finally we see 200. Header contains X token admin. The domain is testsni. Correct server certificate is used, and endpoint is a header. And we got HTTP response with header info. So this is a successful case. We also have X token passed as HTTP header request. This is how you can configure and validate the section 8.4 authorization using HTTP header and also endpoint, path, and also host. So these are three conditions as AND condition. Next, section 8.5, we're going to enable end user authorization by source IP. So here's a precedence order of deny and allow policies. First, if there are any deny policies that match the request, deny the request. This is the first priority. If there's an explicit deny, even if there's allow, it's going to be denied. If there are no allow policies for the workload, allow the request. So this means that you don't need explicit allow. If there's no deny, and if there's no allow, there's nothing, then it's implicit allow. Third, any of the allow policies match the request, allow the request. So this is when there's no deny, but there's explicit allow, deny the request. So if there's no deny, if there's no allow, if it doesn't match anything, it'll deny the request. So fourth, everything else, deny the request. Okay? So what we're gonna do is first get our own IP. So what we're gonna do is to make a curl request to this HTTP bin/IP to get source IP address. And then we're gonna save that as a shell variable called client IP. And then after that, we're gonna do and. If this command is successful, then echo variable. Now IP is returned, which is good. So here we have another authorization policy, deny IP. Action is denied if request source is this IP, which is this one. So what we're gonna do is before applying again, first we want to delete previous authorization policy. So we're gonna do copy this command, and create a shell, paste, and then enter. Clean up, and then go to ECL config, authorization policy, nothing, okay. Next we are going to create this authorization policy by passing this content from std in. And then we are setting this client IP from a shell variable. Basically, it's going to block requests from source IP specified by this variable value. So copy this entire block of code and then enter. Okay, now it's created. So refresh. And now we see authorization policy, deny IP. And now it's going to block if request source is this IP, which is my IP. We've done that from this command. So what we're going to do is to try to make a request to IP, clear shell, and paste in curl IP-b-l-k, enter. And now we see 43 forbidden because we have blocked IP from our IP address. So RBAC access denied, which is okay, all right? So this is how you can blacklist some of the IP addresses by explicit deny. This is the end of this section. Okay, so chapter 9, we're going to be working on ingress security using service entry for external DNS name outside of service mesh. So there are 3 different modes for egress traffic. Default for demo profile when we installed ECL in chapter 2, we allow Envoy proxy to pass through outgoing requests to the services that are not configured inside the service mesh. So let's think about Kubernetes service, and all the Kubernetes services inside Istio service mesh are automatically added to Istio service registry. However, let's say one of the pods inside the Kubernetes cluster wanted to reach external DNS like www.google.com. By default, egress traffic to external one outside of the service mesh is allowed by using path through, passing requests through. Second mode is configure service entries to provide controlled access to external services. This is what we're going to use with service entry. Basically, if we mark those external public DNSs, it could be public DNS or could be private DNS inside, let's say, VPC. It could be in a GCP's private network as well. It doesn't need to be public, but it could be external DNS. But if we mark them by registering them using service entries, we get monitorings, metrics, and also we can control those egress traffic. Last mode is to completely bypass the Envoy proxy for specific range of IPs. So this is going to basically avoid going through Envoy proxy for egress. So there's no way to track metrics and monitor and also control the egress traffic because it's not being intercepted by Envoy proxy. So there are 3 different modes. And here, allow any is the default value, allowing you to start evaluating Istio quickly without controlling access to external services. So it allows any egress connections to go through Envoy proxy. And allow any is the default value, allowing you to start evaluating Istio quickly without controlling access to external services. So this is a default one. So this is the first one without second one. With the second, if we register external DNS with a service entry, we get extra monitoring and control. But without creating service entry, all that egress traffic are allowed. So it says, however, by default, you're gonna lose extra monitoring and control for traffic for external services if you don't use service entries. So we're gonna test that, and eventually we're gonna create a service entry. So first, we're gonna test default pass-through for egress. So we're gonna get a shell inside a curl pod in non-istio namespace. Not this one in the default one, but in non-istio namespace. So grab this command, copy, paste, enter. And after that, we're trying to curl google.com, enter, and 200, which is expected, right? Let's go to k8s dashboard, click graph, namespace, default, and also non-istio. Let's select just the non-istio namespace, okay? Refresh, and let's send the request again, multiple times. We should see curl container showing up, curl pod, non-istio, traffic animation, security, and response time. So we see that because there's no envoy proxy, there's no sidecar injection enabled, we don't get any traffic metrics or monitoring. We don't know where the request is being sent. Whereas if we do, let's say, get a shell inside curl pod in default namespace, which is this one, which contains Istio envoy proxy, we can make a curl request to Google and we can see traffic flow, right? So we are doing it from default namespace where Istio injection is enabled. So go to default namespace. We should see curl pod, uncheck non-Istio, and we should see curl. Okay, display, check off unused nodes. These are just nodes. So we should see curl pod somewhere. Okay, yeah, we see here curl, right? So we can send a request again multiple times, and we can see traffic flow from a curl pod. Refresh every 10 seconds, should show up anytime soon. So we have a curl, right? And also traffic animations enabled. So we see here 48 milliseconds. Now we can see traffic is flowing from a curl to path through cluster. And now we can see at least traffic animation and some metrics, because in this curl pod there's an envoy proxy, whereas in non-Istio namespace we couldn't see anything because there's no envoy to intercept traffic. So this is a default state, path through cluster, but we don't know where request is being sent because google.com is not registered in Istio service mesh. Next section, what we're gonna do is to register external URI using service entry. So this is what we talked about. Second mode, configure service entries to provide controlled access to external services. So before, we are still able to access external site. So this time, let's curl hpbin.org/headers. And this should return HTTP request headers. So enter and return these stuff, right? Now after, we are going to create a service entry to allow access to external HTTP service Google and hpbin.org. We're gonna be using a new custom resource called a service entry, and name is external Google. Host, we're gonna add external host name here. It could be google.com or www, but one note is that these list of hosts need to be fully qualified domain name, which means we cannot use wildcard. So under ports configuration, we add 80 and also 443, and then location to be mesh external, meaning that this does not exist inside Istio service mesh. We're gonna add another service entry called external HTTP bin. We have internal HTTP bin pod, but we are going to be adding hpbin.org. This is a publicly accessible website. And in terms of ports, we have 80, 443, and the location to be external. So we have this YAML file, so we're gonna apply this. So copy this command, exit out from a shell, create a shell, paste, and then enter. And then after that, we're gonna get a shell inside this curl pod again in the default namespace, and then curl Google again, just like we did last time, multiple times. And what we're gonna see is that this path through cluster is gonna be changed to google.com service entry icon, because now we register google.com as one of the service inside Istio service mesh. So we no longer see this generic path through cluster. So refresh, we should see different new diagram. Yes. So let's take a look here. So curl is going to external Google. This is a name that service entry we defined here, external Google. So we know that where it's going actually, as opposed to this kind of a black hole where we don't know where it's going. Same for this one, HB bin. Okay, so we now know that request is going to external Google. We can make a request again, and also we can make a request to HBB org as well. So access HBB org header multiple times. So now we should be able to see two service entries, and the request is flowing from curl to external Google and the external HTTP bin. Refresh. Yep, we see two service entries now for external one. Then we see that it's specific to these hosts as opposed to generic one. And if you click legend, this represents service entry. This is what we can do with a service entry. And notice that in the header returned, this one, envoy decorator operation. X envoy decorator operation is added by Istio sidecar proxy from HTTP response. This is added if request is sent from envoy proxy. And now we can check Istio sidecar proxy's log inside the curl pod. We can execute this command from here, kubectl logs curl. This is the name of the pod, curl, and -c to select the container as Istio proxy, and then pipe tail to get the last one. So exit out from the shell, clear, and then paste kubectl logs curl pod and Istio proxy container, and then we see list of log entries here. We have accessed HTTP bin org and also google.com. So these are now tracked because we are making requests, egress requests from inside the curl pod, which has Istio envoy proxies. Also, we can make a request to apple.com. So go get a shell inside the curl pod again and make a curl request to apple.com, which is not part of Istio service mesh. We can still access it, but exit out, get logs again. Now we see, one more time, now we see apple.com, right? As well as hbb.org and also www.google.com. So notice here, outbound 80 google.com for Google, whereas pass-through cluster for apple.com. So here, take a look here. For apple.com, which is not part of our service entry, we just see pass-through cluster. As opposed to for HBB bin, we have outbound. So we are looking for HBB bin and outbound something. So yeah, outbound 80 HBB bin org. Whereas this one, apple.com, it was pass-through cluster as opposed to outbound. So this is the difference. We have pass-through cluster and also specific external URL. Next, section 9.2, we can set timeout for external service. So similar to inter-cluster request, Istio routing rules can also be set for external services that are accessed using service entry configuration. In this example, you can set some rules like custom timeout rule on calls to external hbbin.org service. So in virtual service hbbin timeout YAML, we're gonna set custom 3 seconds timeout on external calls to hbbin.org. So this is the one, kindness virtual service, name is hbb.org. Host, this is the external one. So this can be either Kubernetes service name inside the service mesh or external one, and then under HB configuration, we set timeout 3 seconds and destination to be host hbbin.org. This can be internal or external. So we're gonna execute this one. Virtual service is actually in this folder, so it's under 9, virtual service hbbin timeout. kubectl apply -f virtual service hbbin timeout YAML. Now it's configured. Let's get a shell inside the curl pod inside this namespace. So copy this kubectl exec-it curl sh, and then let's make a curl request to http bin.org, and then endpoint is going to be delay 5. This means this website is going to return after 5 seconds. And we are wrapping this command with a time command to show stats of how long it took to get response. right? So this is gonna sleep for 5 seconds and then return. It says 5:04 gateway timeout, and it returned approximately 3 seconds after. This is because of a 3 seconds timeout introduced with a virtual service, and therefore it returned 5:04 gateway timeout. So as explained here, this time 5:04 appears after 3 seconds. This is the timeout configuration from virtual service. So although HBB org was waiting for 5 seconds because of delay 5 seconds, it still cut off the request at 3 seconds. Alright students, so this is the last chapter in this course, chapter 10, observability. So we will demonstrate how to collect telemetry information from the mesh. We have already been using k8s dashboard quite a bit. I'm going to also introduce a new dashboard called Yagar. This is the free request tracing dashboard. You can have an alternative for this one like a Datadog APM for request tracing, but this comes with Istio if you use the profile demo when you install the Istio in chapter 2. Section 10.1, we're going to access Istio envoy proxy log. We have done this multiple times either from k8s or from console as well. And this is enabled for profile demo by this line, mesh config dev std out. So where is this file? We can go back to chapter 2, generated manifest, and also profile demo config. And let's search this line, search, and here, mesh access log file, dev std out, and new another second file. Do we have that one? Yes. So mesh config access log file, dev std out. So this is part of a profile demo config. So this is already enabled for profile demo. We can access / product page through Ingress gateway. So what this means is that product page is exposed using a gateway, and a gateway service of type load balancer and Kubernetes actually created AWS EOB in k8s example. So what we can do is to make a curl request 5 times using a for loop in a bash. So from I1 to 5, make a curl request to / product page. After that, we can get a log from Istio sidecar proxy by selecting container name by -c Istio proxy. So let's do that. We can make a request, paste here, enter. All right, and afterward, we're going to do kubectl logs, and then we're gonna get this pod name product page by label, which is gonna be this one. And then after that, we're gonna select -- container option and the Istio proxy, and we're gonna do tail. So pasting, enter. We're gonna access this / product page endpoint through Ingress gateway. So we're gonna do is to use a bash for loop for I from 1 to 5, make a curl request to AWS EOB's public DNS name / endpoint, and don't forget to pass -l -k because we enabled HTTPS redirection at the end of chapter 7. So copy this command and paste and enter. And now we see requests are being sent and responses are being shown here for 5 times. It's getting a 200 requests because we see HTML content. We can see that from a k8s diagram as well. So here we see traffic flow from Istio Ingress gateway, the product page, and reviews and v3 and whatnot. This is okay. And we're gonna get logs from Istio sidecar container. So we did kubectl logs for pod by selecting pod using -- label app product page. We're gonna basically select this product page blah 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 pod name, and then after that we added -- container Istio proxy so that we get logs from one of the 2 containers, and then we did a pipe tail, and the output returns something like this. So / product page, and we have 200, 200, and a / product page / reviews because actually it's making a request. This is the product page is the incoming, and this is outgoing from in terms of from Istio sidecar envoy proxy's perspective. It'll intercept both incoming and outgoing. So this one is from a load balancer or gateway, and this is behind. So this is from a product page backend reviews. So we see that request intercepted and logged in the envoy proxy container. So next, 10.2, distributed tracing with Yaga dashboard. So I think we haven't really used this one so far in this course, but Yaga is already installed when installing Istio using demo profile. The number of requests you see on Yaga depends on Istio sampling rate. You set this rate when you install Istio, and the default sampling rate is 1%. So let's open dashboard by Istio CTO dashboard Yaga. So copy this command, create a shell, paste, Istio CTO dashboard Yaga, and it's going to open up Yaga dashboard. All right, so it's making a port forwarding command from localhost 590 to remote Yaga pod. And then here we have drop down list. Click this one, and let's say we select product page in default namespace, and then click find traces button at the bottom, because we have sent at least like 10 requests so far. So we now see timeline with bunch of requests, and also kind of a distribution map of latency, 40 milliseconds, 50 milliseconds. So right now, the most recent one is this one. This is a time X, 9080 product page, and then we see a row or table here. And this one is latency was 51 milliseconds, 33, and 34, and this is by time. So this is ordered by time. Top being the most recent one, 641, by 16 seconds, 13, 10th, right? Because we are making 5 requests from for loop. So what we can do is click this one to expand. This is still ingress gateway. It lasted total 51 seconds, right? So this is when incoming request hit ingress gateway, and this is where it returned back. But internally, it was making other requests. So next one, ingress gateway passed request to product page. If you click this one, you see product page, and you can expand a little bit more. We have like HP request content here. And if you go back one more time, because this wasn't complete. This one is complete because you see ingress gateway, details, and then product page, ratings, and then reviews. This one somehow didn't make request to backend. So let's click this one. You see this is a distribution of traffic and also latencies. This one is total span. This is kind of like what you can see in Chrome developer tools. And the next product page is kind of like a subset of it. It's like 50 or 29 milliseconds. And the product page actually called the details for 1 millisecond. And also product page also called reviews. So this is in order from left to right. So first called the details, next called the reviews, and the reviews called ratings. So in this way we can kind of see kind of like X-ray vision of which microservices are taking longer time. So this is kind of request tracing. So if you right click and do inspect on this book info YAML file, we have done this one before. Inspect network, and then from here refresh this page. You're gonna see product page with latency here. It's gonna show up here eventually. It's taking a long time, right? 10 seconds. One more time, let's do that. This time product page 300 milliseconds, but you don't know what other downstream microservices are being called, right? Because they are hidden behind this product page. So you don't get the entire view about microservices distributed request tracing. You only see first one product page. We are supposed to see more services here, and that's what Yoga makes it possible. See, backend, you can see a lot of traces, metrics, and latencies, and also HTTP headers passed, right? So if you click on, let's say reviews, tags, this is a HTTP header probably, and process. Okay, so you can see a lot more information. This is not really a complete tool for production use case probably. There's another one called a Datadog. This is the paid version, but Datadog APM has service maps. So probably that's better to use as opposed to this kind of free one. And then lastly, we're gonna do visualize service mesh using TI. We have done this multiple times while we were working on enabling other features. So I don't think I need to explain this anymore because we have the topology with service mesh, latencies, and also TLS connection. We can enable that from this display drop down, traffic animation, security, and if we send traffic, then we're gonna see some request animation, refresh, and we should see a request going through. And also, we've also talked about Grafana in chapter 3. Grafana is more related to Kubernetes clusters metrics. So not really low-level details about what's inside microservice service mesh architectures, but tells us more about metrics about cluster nodes, how many pods are there, and the memory and CPU usage and whatnot. So again, this is a kind of a recap, but go to dashboard of Grafana as we have done in chapter 3. So nothing much more to talk about in regards to service mesh or Istio for this Grafana. This is more like a cluster-wide underlying infrastructure and also pods metrics, not really for service mesh per se architecture. So that's that. That's it for this section, and this is the end of this course.